I'm really pleased to be here. Um, One of the things I wanted to point out to you is I'm a native Louisianian. And so I want to tell you about some of my history in Louisiana first before I talk about my science. And Dr. Wachusett said that I'm formerly of the chemistry department, but my favorite title, I have a number of titles, my favorite title is professor, not vice president. But that's because I interact with students, and that's my true love. And even when I retire, that will be the thing that I'm doing, interacting with students, working with students. So I indicated I'm a native Louisianian. I think we know, how many of you are from Louisiana? No one from the other site is from Louisiana, I guess. Can they help me? Oh, okay. They can hear me then. They're responding. And so we know where Louisiana is on the U.S. map. I was born in a little town called DeQuincy, Louisiana. Any of you know where DeQuincy is? Yeah. If you're from Lake Charles, you certainly know where DeQuincy is. DeQuincy is somewhere around here, about 20 miles from Lake Charles. However, that's not where I was raised. I later, oops, sorry about that. I later moved to Avoyelles Parish. And any of you know any cities in Avoyelles Parish? Most people have heard of Marksville. Well, I'm from another little town called Bunkie. And when I grew up, I had many mentors, but my primary mentors were these guys, the cotton fields. I used to work in the cotton fields. We've been complaining about the sun and how hot it is, okay? Well, it was just as hot when I was young. Can you imagine working out in the cotton fields on a day like today or a day like yesterday all day long? Get up at 6 o'clock in the morning, you're driven to the cotton fields, and you come back home about 6 o'clock. So 12 hours continuously. You get a half-hour break for lunch. You bring your own meal, your own sandwiches. And then you take that half-hour break and you work straight through. So the entire time I'm working, these cotton fields kept saying to me, go to college. Go to college. And I say, I hear you, because I was determined that whatever I was going to do in life, it wasn't going to be anything related to working out in that hot sun in Louisiana. And so I ended up going to college, attending Southern University across town. I think most of you know where Southern is. I graduated, first of all, I graduated valedictorian of my class. I had a full scholarship to Southern. And back in those days, you know, if I tell you what a full scholarship was, you won't believe it. Full scholarship was $3,200. That paid everything, including housing, meals, and everything. $800 a year. Unbelievable. But that's the change in times in terms of money. So I had a full scholarship to Southern, and I'd gone to a summer program, and Dr. Vanden White, chair of the chemistry department, said, if you major in chemistry, you can skip the first year of chemistry. Sounded like a good deal to me. So I skipped the first year of chemistry and went on to take some advanced chemistry course, advanced mathematics courses in my last year. I love mathematics, so if I hadn't been a chemistry major, I probably would have been a mathematics major. So when I finished Southern, a company that was a prime contractor for the Atomic Energy Commission offered me a job. But that was clear. If you look at where I had to fly, that's clear across the United States, about as far as you can go. Even if I'd gone up here, it's probably not as far. It's about as far as you can go in the continental United States. So that was in Hanford, Washington, or the Tri-Cities, as it's called. Anybody know the history of Hanford? For many years, Hanford was not listed on the map. Anybody know why? Any of you know? No, it wasn't too small. Pardon? It was government, but why? Pardon? Well, it had to do with atomic energy, but let me tell you, there are two other cities who were not on the map: Oak Ridge, Tennessee, Los Alamos, New Mexico. Okay, that should give you a hint. Had to do with the atomic bomb. Hanford produced the fuel, and Oak Ridge processed the fuel, and Los Alamos have produced the bomb for World War II. And so many years this, but then when I went to work there, they were working on reprocessing the fuel and what to do with all this contamination that's now leaking into the water table now and all of that. So I worked on solidification methods. And so I worked there for 5 years before deciding that, I don't like being a technician. I want to go into graduate school and get my PhD. And so I went to the University of Washington. If you ever been to the University of Washington, our campus is very beautiful. University of Washington is one of the most beautiful campuses in the world. Because if you look at this fountain right here, this fountain is right in front of the chemistry building. The chemistry building is over here somewhere. If I get on the other side of this fountain, and on a clear day, I'll see something that's very surreal. How many of you have been to Seattle? What's the most surreal view in the Seattle horizon? What? Yes, the mountain. What mountain in particular? Mount Rainier. It is absolutely gorgeous. And I keep intending to incorporate a slide so you can see what I'm talking about. I mean, it's like something out of mystical vision of some sort. I mean, just the most beautiful sight you can see. I love Seattle. But school sooner or later comes to an end. Average time for a PhD was 5.5 years. I told my wife, let me work as hard as I can. I'll get out in 4 years. I finished in 3.5 years with a PhD in a program that typically was at least 5.5 years. And so my first job was coming back to the South, and a little place called College Station, Texas. What's in College Station? Any university you ever heard of? Texas A&M. That's where my first job was. I was working at Texas A&M, and I worked there for 5 years, got early tenure, and then move on to another university in Atlanta, Georgia, a small private university. What's the most famous small private university in Atlanta? Private. Georgia Tech is public. Pardon? Private. Wealthiest. Emory University. Surely you've heard of Emory University. Very exclusive. Emory's endowment back when I was there was $2 billion. I imagine much higher than that now. But I was on the faculty at Emory for 10 years. And LSU had an endowed professorship and heard that I was from Louisiana, so they recruited me back here with that endowed professorship. I'm the West Professor of Chemistry. So now I'm going to talk about my research. And so I didn't realize this order was going to be very biomedical, but I'm going to talk about biomedical applications. Then all of a sudden at the end, I said, well, maybe the audience will be completely biomedical. So I added another slide, which is not biomedical. So at the end, if I have time, I'll talk about that. But I'm going to talk about nano gumbos. And I know what's conjuring in your mind when I'm talking about gumbos, right? How can you make gumbos nano? Well, I'm going to explain that. I'm working in an area called ionic liquids. Ionic liquids are just as the name implies, the liquids which are ionic. For example, water. Water is not an ionic liquid because water is a series of molecules, right, that have this fluid state we call liquid. In the case of ionic liquids, they are really made of ions that have the same kind of fluid state as water. Quite often they're very viscous, much more viscous than water, but they have a fluid state, which is unusual. because the typical sort of ions we think of are typically solids. But when you put together species like this, they're organic ions. Typically, you have organic compounds with, non-isolated charges, and then some inorganic compounds or incompatible compounds that will cause these to be liquids. Because in the case of sodium chloride, which we know is a solid, right? The sodium and the chloride ions are of nice size and compatible so that they stack together properly. And so they form solids, very high melting solids. Do you have an idea what the melting point of sodium chloride is? Well, it's over 800 degrees C. It has a high melting point. Why is that? Because this lattice structure is so stable. In order to break it and make it fluid, you basically have to break these molecules apart. Now, at 800 degrees C, sodium chloride becomes an ionic liquid. Okay? It is it's a liquid made of ions. But that's not practical. If we wanted ionic liquids or liquids, we want them low melting liquids, right? So ionic liquids are typically defined as a series of liquids made of ions that have a melting point less than 100 degrees C. So about the boiling point of water is the usual definition. Okay? The fact that they are less than 100 degrees C, between 25 and 100, they're solids, right? Because room temperature, obviously, they're going to be solids all the way up to 100 degrees C. Now, why are they liquids? Because the ions that are in this mixture or in this molecule, these molecules are not very compatible in terms of stacking. Okay? All right, so you have a positive ion and a counter ion, and they don't stack very well. So if they don't stack very well, they slide over each other. They're liquids. Okay? And so they're low melting salts. That's typical with ionic. So what are the properties? They're non-volatile, high thermal stability, high ionic conductivity. In other words, they conduct the current. They're highly solvated. Very strange properties. You can make ionic liquids which are both polar and nonpolar. In other words, they will dissolve polar compound, same ionic liquid, as well as nonpolar compound. You can make ionic liquids that are selectively soluble. You can make an ionic liquid, and this has been done, that is insoluble in water, soluble in methanol, and insoluble in hexane. That's counterintuitive, right, to our freshman chemistry that we've learned. How can something be soluble in a more hydrophobic solvent and then insoluble in an even more hydrophobic solvent? So these are kinds of strange properties, these molecules. They're recyclable because you can use them as solvents and then recover them. And they're tunable. We can simply take the ions and change the ions and make them have very different properties, ranging from hydrophilic to hydrophobic. Just by changing the ion, I can make a compound hydrophilic or I can make it hydrophobic. That's not the traditional way we think of changing the hydrophilic and hydrophobicity. The applications of these compounds are numerous. I mean, you can think of any area of science or engineering these compounds have been used. In the analytical sciences, as solvents, in the biological sciences. And these are just a limited number of applications that I decided to list. There are many more applications than this that are too numerous to list. Energy and engineering areas. All of these areas ionic liquids have been applied to specific kinds of uses. I wrote an article just recently on perspectives of moving ionic liquid chemistry into the solid phase. I worked in this ionic liquid field for a long time, and then I said, wait a minute. If I could take the same chemistry and move it into the solid phase, I would have materials chemistry that I could manipulate its properties simply by changing the counter ions. Now, I thought I was jumping off of a cliff because changing your area of research on the basis of a hunch is very dangerous. Dangerous for you because it could mean the end of your career. Dangerous for your graduate students because they're running behind you to jump off that cliff. Or my postdoc, okay? Turns out this is the most interesting thing I've ever done in my life. Done lots of research. This is the most interesting thing I've ever done and the most exciting time of my life in terms of my research. And so let me explain to you why. I call these compounds, new compounds, gumbos. And remember I talked about nano gumbos, so this is what you guys were thinking about. These are not the gumbos I'm talking about, okay? It's just an acronym that I developed. And there are new kinds of gumbos. They're referred to a group of uniform materials based on organic salts. And if you take that acronym, it spells out the word gumbo. Now, I get all kinds of headaches from reviewers. This is ridiculous. This name does not, these compounds do not remind me of the wonderful soup I eat when I go to Louisiana. Well, that was not my intention. Or, this is absurd. Why doesn't this guy change this name? Well, when you invent something, you can call it anything that you want to call it. Okay, I have a patent pending which is about to go through on this. And I can call it whatever I want to call it. I can call it the most absurd name you can think of, right? Rice University developed some nanoparticles that they call nanorice. They have nano, and one of my colleagues said, why don't you take that nanorice, mix it with your gumbos, you have a wonderful concoction. I thought that was ridiculous, but it was funny. And so most gumbos are frozen ionic liquids, melting point greater than 100 degrees C, but less than 100 degrees C. In other words, they're solid phase material. But I've extended the melting point up to 250 degrees C. So they get outside the range of frozen ionic liquids. So I had to come up with a different name. Because if I use the name frozen ionic liquids, people would think I'm talking about 25 to 100 degrees C. But I'm going all the way up to 250 degrees C. They have tunable physical properties just like ionic liquids because simply by changing the counterions, I can change them. I can prepare them to be functional, bifunctional, multifunctional. And so here's the overlap range. Ionic liquids go up to 100 degrees C. Gumbos go from 25 to 250 degrees C. And so frozen ionic liquid and then these solid phase organic ionic materials. So quick gumbos tutorial. They're strictly solid phase compounds. I'm not talking about liquids. Properties can be manipulated through formation of composites or changes in the ions. Right? Solubility properties can be changed by simply changing the counterion. I'm going to give you a real nice example of that. Can have selective soluble and all of these other kind of properties I talked about for ionic liquids. Those can also be true for gumbos. Can be easily made to be multifunctional, easily designed for particular uses, and since they're solids, I can convert them to nano gumbos. Who knows what a nanometer is? What? Right, 10 to the minus 9 meters, right? So it's a nanometer. Now, to give you some concept of what that is, if I had some hair on my head, I could pull one of those hairs out and split it widthwise into 100,000 equal pieces. Take one hair, split it into 100,000 equal pieces widthwise. One of those pieces would be a nanometer. That's how small a nanometer is. Now, you can barely see a hair, right? You have to use a microscope to see it well. Can you imagine 1/100,000th of a hair? That's how small a nanometer is. And so we developed techniques to make these nanoparticles. Our first was published in a journal we call Nanoletters, one of the highest rated journal in the American Chemical Society. Impact factor of greater than 10, probably 12 or so. And we've developed other techniques for making these nanoparticles. These are we're using a scanning electron microscope to see these because you can't physically see these. But this is my student, Susanna Hamden, who just finished her PhD in May, who developed these procedures for making nanoparticles. She's the expert in my group for making these things. These are about 20 nanometers, 19 plus or minus 2 nanometers. And you can see they're fairly reproducible, but they're organic salts. So we started studying these compounds. Little did we know how many properties. We knew that properties would change for metals when you get down to this small region. And there's a reason metals change properties, right? Because when you start making the particles smaller than the bandwidth of these metal particles, then the quantum effects kick in and you get these very strange properties. That's not necessarily true for organic compounds, but in fact, we did find some unusual properties, and I'll talk about. We can even make GUMBOS nanotubes. I won't talk about how we made these. But here's another paper, another journal, Journal of American Chemical Society. Again, one of the most prestigious journals in the ECS. We recently published a paper. And the title of the paper was Tunable Cytotoxicity, Rhodamine 6G by Anion Variation. Okay? And this was done by Paul Magoo. The work is being continued by Namisha Bhattarai, and we're consulting with Dr. J. Michael Mathis over in the vet school. Now, traditionally, if you want to change the hydrophobicity of a compound, let's say crystal violet, you want to make it more hydrophobic, you put different appendages on it which are hydrophobic, right? You want to make it hydrophilic, you put different appendages on it which are more hydrophilic. So these compounds to the left are more hydrophilic than crystal violet. These are more hydrophobic. And you can look at the log octanol water partition coefficient. Basically, what that measures is octanol is a very hydrophobic solvent. Water is very hydrophilic. So you're measuring how well these compounds partition into octanol or water, the relative ratio. The more they partition into octanol, the more hydrophobic they are. The more they partition into water, the more hydrophilic. Right? And so you can see where the log octanol partition coefficient increases going from left to right. When they're negative, right, that means they prefer water over octanol. When they're slightly positive, they slightly prefer octanol. When they're, this is log 10, right? So this is 100 times, more than 100 times, well, they prefer more than 100 times more to be in octanol than water. Okay? But in ionic liquid chemistry, there's a different approach. Remember I told you the synthetic approach, you're changing these compounds, but they're different compounds. When you're adding all these hydrophobic groups on them, that's not the same compound, right? Or all these hydrophilic compounds. And then you're going to do tests and compare those compounds. You're comparing different compounds. You're not just comparing the hydrophobicity or hydrophilicity. You're comparing compounds that are different. However, if I change the ions, I can say that the cation is the same. Okay? But in ionic liquid chemistry, I can change the ion to make them hydrophobic. And I'll show you an example of this. Here's the compound rhodamine 6G. Okay? If you look at this part of the structure, it is a xanthine-based compound. If you look at this part of the structure, it's another compound that I can guarantee you all of you have seen before. What is that compound? Anybody can tell me? In the square brackets. Suppose I tell you that you go to a industrial show and they have a liquid in a bottle and it's very green glowing liquid. What is that? Or you go to a doctor and the doctor, some of you are not old enough to have this test, but he wants to test your eye, the pressure in your eyes, and he put this greenish orange liquid in your eye. You know what that is? This dye. Pardon? Can't hear you. Somebody said. It's fluorescein. Fluorescein, right? And so fluorescein, rhodamine is really a derivative of fluorescein, right? Which is originally a derivative of xanthine type compound. So here's the rhodamine structure. And people have studied this compound for years and years and years. And in terms of the toxicity to a normal and cancer cell, the only conclusion they come to is that this stuff is toxic. It kills normal cells, it kills cancer cells. So it can't be used, not easily used, as an anti-carcinogen or anti-cancer agent, right? A cancer therapeutic agent, because it kills normal cells. And in fact, most compounds that are cancer therapeutic kill normal cells. That's why people get so sick. But they tend to be selective for cancer cells, and that's why they can use them. So after all those studies, it is toxic to both normal and cancer cells. Well, what we did was take rhodamine 6G, convert it to gumbos. We're going to change the counterline, and we're going to test it against cancer cells. We did not expect the results we got. And so here are the log KOWs. You see that the chloride form. The reason people have gotten these toxicities, they just take it off the shelf and test the toxicity and say this compound is toxic to everything, never thinking the counterline might have an effect. And so this is the compound, which is very hydrophilic, that they test. We changed the counterline and we changed the hydrophobicity. Notice that this compound we call Betty, whose structure is right here, is very hydrophobic, and it prefers octanol almost as much as it does water, because its KOW is almost 1, right? So it's hydrophobic. And so here are those numbers again. And in fact, the most hydrophilic one is ascorbic acid as the counterline. Here's Betty, which is hydrophobic. And let's look at the chloride. The chloride, which is normally tested, is not quite as hydrophilic as the ascorbate derivative, but it's in between here. It's over on the very hydrophilic end. So what they were testing was a compound that was very water soluble. We're going to test Betty and see what happens. When we introduce the rhodamine Betty compound, this is normal cells, and these tails are characteristic of the normal cells, whereas the cancer cell, now these two cells are from the same cell line. This is a cancer cell from the same cell line as this one. And this is another breast cancer cell line, but from a different cell line. You notice that all of them take on the rhodamine 6G Betty, but it seems to be more concentrated in the cancer cell. Well, that's interesting. So it'll probably kill both of them. So we take the chloride and we test it against the normal cell, we test it against the cancer cell of the same cell line, and we test it against the aggressive cancer cell, the green one. Okay? And what happens? It kills everything. It kills normal cells. What this is, the cell viability is a function of concentration. And so as the cell viability decreases with concentration, that means that compound is toxic. In contrast, when we take the Betty compound, look at what happens. Normal cell lines, you have normal variations that are within, a single standard deviation, but it stops killing the normal cells. It only kills the cancer cells. We were shocked at that. Here we have simply changed the toxicity by changing the counterline. And so what is the mechanism? Well, we're making hydrophobic compounds, and so they're probably attached to cancer cell walls. Cancer cell walls are known to be very hydrophobic. And aggressive cancer cells, we speculate. When I put a question mark, these are not certain, but these are speculations. Aggressive cancer cells are even more hydrophobic. Easy penetration of nanogumbos through endocytosis. You know what endocytosis is? Simply a mechanism by which particles are engulfed into cells. And there are 2 or 3 different mechanisms of endocytosis. We've studied them. We know the exact mechanism. So we know that this is accurate. It allows easy entrance into the mitochondria because we found out that our Betty compound kill the cancer cells by the same mechanism as the chloride compound. It gets into the mitochondria. It inhibits oxidative phosphorylation and stops ATP production. ATP production is the energy of the cell. If you stop the energy of the cells, cells die. So they kill by the same mechanism, but why is Betty only killing the cancer cells and not killing the normal cells when we see that Betty is getting inside the normal cells? That's another question that we're trying to answer. Lack of interest in the mitochondria for normal cells result in cell death for cancer cells. Now we send this off, we know we're going to get some money from NIH for this. They're going to just roll up the table and just dump all the money in our lap and say, you guys just go ahead and do this wonderful research. Not true. We get all kinds of speculation. Does this process work in vivo? You show it works in a petri dish. Does it work in vivo? No, we don't think it's going to work in in vivo, in a real live animal. That's what they kept telling us. Well, we decided to do these studies with Dr. Mathis. So I'm not going to talk about this. I interjected some other studies, but basically we're developing organic light-emitting diodes from these compounds. And just want to acknowledge the support of the National Science Foundation and be glad to answer any questions you might have. Yes.
You had mentioned that in those mice studies, after about 2 weeks, all of the compound was out.
Not all of it, but it was beginning to eject all of the compound. We suspect if a mouse had not died by then, it wouldn't die.
And what were the comparisons of the tumor sizes?
We're doing more. That was just an arbitrary study that we did just to see. We're doing more detailed tumor studies. As a matter of fact, I talked to my student this morning. She has about a dozen mice, and she's injected tumors, and they're waiting till the tumors get of an appropriate size. So we're doing a more systematic study with the tumors right now. We haven't gotten the results. That was just an off-the-cuff experiment just to see what would happen.
Anybody else here?
Let me ask the remote site. So, folks, Primate Center, any questions? Shreveport. If you do, make sure you're on mute. Any questions? No? Wave at us at least. I'll get it later. New Orleans, any questions? You may have to unmute you. Any questions? No? All right.
All right. Any more questions from here?
So when you inspected the organs, did you find any damage from the compound?
I don't have the results for that yet. I'll have to talk with my student. But we didn't do a detailed analysis yet, but just visually there wasn't any damage to the organ. We're going to do a more detailed analysis after we do these current studies. Most of the other studies was just if the premise was that it works in vivo and it didn't work here, we probably weren't going to pursue these studies in more detail. But we just did these studies initially just to see if it does work, and it's very promising. So now we have to go back and do more detailed and systematic studies. And hopefully those results will be available within a month. You can email me if you want to know the results.
All right. Join me again in thanking Dr. Warner. Thank you so much.